Hi, this is going to be a note presentation on intermolecular forces, IMFs, and how they affect different properties. So if you guys remember, we've learned now about our three types of IMFs, London dispersion, dipole-dipole, and hydrogen bonds. So the properties we're going to talk about today, I'll show you it very soon, but things like the melting and boiling point, or why does something dissolve and something else doesn't? Um, why do certain things, yeah, anyways, I'll leave it at that. So it really has to do with the particular substance that we're talking about. The number of IMFs and the strength of those IMFs are what will affect the properties. So the properties that we're going to look at today are like changes in state. So when you melt something and boil something, you have to break those IMFs in order for it to go from a liquid to a gas, or from a solid to a liquid. We're also going to look at viscosity, which is the resistance to flow. Like think about honey or certain types of oils are really thick. Solubility, whether something will or won't dissolve. And then also surface tension, which is kind of what you see like when you have a really nice waxed car, how the water beads up. So we will talk about all of this. So changes in state like boiling and melting, here would be an example of the water and the hydrogen bonds that it has. So the hydrogen of one water is going to be attracted to the oxygen of the other. And this is going to happen in many different directions. So if we were thinking, like this is a liquid and we're going to have this change to a gas or boiling, all of these have to be broken in order for the waters to be able to escape. So this is why water has a really high boiling point at 100 degrees Celsius compared to, and I have a typo here, but I'll fix it. The H2S is a really similar size molecule and its boiling point is negative 65. So it's a huge difference. So the fact that it has the stronger IMF of hydrogen bonds is why it has a higher boiling point. H2S for sure doesn't have hydrogen bonds. I'd actually have to figure it out. It either has dipole-dipole or just LDF. Also, if you look at group 17 in the periodic table, the fact that the fluorine and the chlorine are going to have they're all going to have LDFs, but they're going to have the strength of the LDFs are less, so that's why they have a low boiling point. So these are gases, that's why they're red, and then bromine's a liquid because it has more electrons, so the strengths of its LDFs get stronger. And then iodine's a solid, so that's even more. So some IMFs are broken when you go from a solid to a liquid, not all of them. And then all of them have to be broken to go from a liquid to a gas. And that requires an input of energy. So the stronger those IMFs are, the more energy it is required in order to melt or boil, or even just evaporating, slowly over time. Something like water is going to evaporate slower than something like, let's say you have like rubbing alcohol, which we know is really volatile, and that's because it doesn't have very strong IMFs. So viscosity, this is just plain old honey, so it's very thick. Ketchup, things like that. It can be oil, like motor oil. The cooking oils too are usually higher in viscosity than, let's say, water. So viscosity is really the resistance to flowing, and we know that the more the resistance it has, the higher viscosity it has. So honey is more viscous than water is. And that's because the larger molecules of the honey will tend to form more IMFs. And they actually also, because they're so long and big, they actually kind of intertwine and stick to each other. So that makes them more likely to not slide past one another. So when they're flowing, they have to be breaking those IMFs continually to flow, to kind of pass by one another, so they're less able to do that. So the more they stick together, then the higher that viscosity is. So again, that could be, based on the strengths of the IMFs, because these are big, big molecules. Solubility. So this is showing you the little blue things are water, and then the yellow and red is anything like a sugar or salt being dissolved. So in order for something to dissolve, the water has to break its IMFs, and then let's say that was sugar, has to break its IMFs, and then you have to form new IMFs. So when we talk about solubility, we're talking about the ability of something to dissolve. In order for something to dissolve, the solute and the solvent have to break, like I said, those IMFs, and then that are formed between themselves first. So the water has to break its IMFs, and the sugar has to break its IMFs. And then they will form those new IMFs together. Not everything will do this. So molecules that have similar IMF strength will dissolve in one another, but sometimes things will not dissolve in each other. So if the energy that's required to break all of those IMFs, the ones of the water and the ones of the sugar, for example, if those are much greater than how much energy ends up being released in the long run, then those two things won't dissolve in one another. We also know that like dissolves like. So polar things will dissolve in polar substances. So water is usually the polar. So things that are water soluble have some polarity to them. Non-polar things will dissolve in non-polar things, and there's a lot of things around the house that you can use this application for. So like nail polish, once it's on and dried, it's a very non-polar substance, so water isn't able to dissolve it. So that's why you have to use like a nail polish remover, which is another non-polar solvent. My niece, when she was younger, drawed on my hardwood floors with the Sharpie. And Sharpie, if you think about it now, they're permanent markers. So that means that they're not water soluble. You don't want water to dissolve them. You want to keep that writing later, but you don't want someone writing on your hardwood floors with it. So there's lots of different tricks to removing it. And mainly, most of them include some kind of a non-polar solvent, like using an alcohol or an oil, or even writing on it with an expo marker. It's different. You're playing tricks kind of on the solubility and trying to get that non-polar Sharpie to dissolve. Oil and water. So this one, it's messy, but if you've ever added them to one another, the oil will not mix with the water. It will for a little bit, you can see in the right, but eventually, even if you shake it, they will not mix. And the water goes on the bottom because it's more dense than the oil. So they do not have similar IMFs. They are not like. So like doesn't, the water is polar, so that means the oil has to be non-polar. So water has, it has LDFs. It has that really strong dipole-dipole, which we call it hydrogen bonding, and that takes a lot of energy to break. So it can only then form an IMF of a London dispersion force with the oil, because the oil is non-polar, and that requires more energy than would be released. So that is why they are not going to dissolve in one another. So again, if you remember, here's a silly little cartoon, but this is just showing you that the oil is, it's just carbon and hydrogen essentially, which is non-polar. It ends up, the electronegativity difference isn't polar, and it's also kind of a symmetrical shape, so it ends up being non-polar, whereas the water is really polar to the point that we have that hydrogen bond. So they are not alike, so they will not mix. Surface tension. So if you've ever seen like an insect walk across the water, or the water beat up on something, that is what surface tension is. We usually focus on water. It's the resistance of any liquid, but usually water, to spread out. So it's because of those IMFs again. The water has strong IMFs, so they want to stick together and not spread out. So the higher the IMFs, the more that beating up of the water is going to happen. So if we were to have like a pool of something like a liquid, let's say like rubbing alcohol with less IMFs, and then we put the spider on top of there, he most likely is going to sink. Soap and water. So we can't live without soap. And I know we haven't had an oil spill lately in the news, I don't think, but they're super depressing to look at. The wildlife that gets coated, they will die unless someone intervenes and takes that oil out of them, which has everything to do with IMFs. So the oil, just like in the pictures with the cooking oil, this kind of crude oil also doesn't, it's nonpolar, so it doesn't mix with water. So it's not going to come off unless you use something called soap, which is a surfactant. So soap has two parts. It has, it kind of looks like a sperm. The polar head, this part likes water, and then it has a non-polar tail, and that part likes oil. So this also works when we wash our clothes, which can have some oils and things from us. That then it helps the detergent helps pull all that dirt and grease and grime out, and then we can rinse it down the drain. So because of that dual nature of the soap, the fact that it's polar on one end and non-polar on the other, that's why it can interact with water and that other non-polar thing. And what it'll do is actually form this kind of circle, and then surrounds that oil or the dirt or something that's not just water soluble on its own. And then you can flush it down the drain, or, rinse it off that poor little duck or penguin. So the reason, we see why that happens with the polarity of the head and the tail of the soap. It is disturbing the ability of those. Let me think about it. I want to make sure I say this right to you. The surface tension of the water gets lowered when the soap is added. So we could also add that soap to that, the cooking oil and water, and they will mix. We do that daily. Like when I'm washing my dishes at home, there's usually some kind of a oil, kind of butter residue. So depending on what I make, and that I definitely use a lot of soap. So I hope that helps you guys understand how important all of those, the properties of why things do what they do, has everything to do with the bonding, which is then related to the shape, which then ultimately tells us whether the molecule is polar or non-polar and what type of IMF it is. So it's a lot of stuff, isn't it? So I hope you guys enjoyed it, and I will be talking to you soon.